screencast. This is what we're covering in physics next. Remember to email me or contact me for any questions and concerns. Okay, trying to advance to the next slide here. All right, here we go. Vibration of a pendulum. So remember a pendulum, a back and forth motion, that's called a vibration. We're going to be talking about waves, all kinds of waves, types of waves, such as light and sound. They are both forms of energy that move as waves. That is transmitted progressively from one place to the next with no action. The time of the back and forth swing of a pendulum is called the period. Galileo discovered that the period of a pendulum depends only on its length. It was on gravity, and we actually made a pendulum, and we used different lengths of strings, and we played around with masses, but only the length of the string affected the period. Wave description, when we talk about any back and forth vibratory motion, a sine curve, this is a pictorial representation of a wave right here. You have the amplitude is the height of the wave. You have the wavelength is the length of one wave to the next. You've got the top of the wave being the crest and the bottom of the wave being the trough. So as I just said, the height is called the amplitude, and it refers to the distance from the midpoint to the crest from equilibrium. Notice that middle line. The wavelength of a wave is the distance from one top of one crest to the top of the next one. Equivalently, the wavelength is the distance between successively identical parts of the wave. So however you want to measure it, from bottom to bottom, top to top. For vibrations, an object makes in a unit of time is an object's frequency. So that is the frequency. Think of how many when you think of frequency. The frequency specifies the number of back and forth. Used for frequency is hertz, or Hz for short. You can see down the bottom in the picture, you have the highest frequency. Those are the really smushed together ones. So there's a lot in one space, and that would be a high frequency. Medium is in the middle, and low is really spread out. So there's not that many wavelengths that will pass by. Electrons, it's always about the electrons. The electrons are all super important again. Radio station at 960 hertz, or kilohertz actually, vibrate at 960,000 times each second, producing 960 kilohertz radio waves. And again, that's at AM. When frequency is known, its period can be calculated, and vice versa. Makes two vibrations in 1 second. Frequency, one vibration, or the period, equals a half second. So here you have the frequency, the math here, divided by the frequency. So simple math there. Okay. Right here is the math, right there. So look back to this page if you have to calculate the frequency, or if you have to calculate the period. The next one we're talking about is the electromagnetic spectrum. Okay, most information gets to us in some form of a wave. So if it's sound energy traveling to our ears through a wave, or light energy that comes to our eyes in the form of a different kind of wave, an electromagnetic wave, radio and television travel in the form of electromagnetic waves. So looking at the picture down the bottom, you can see the wavelengths here. You see the radio as that really at the end on the left, that has a really spread out wavelength. And then you see the higher frequency of waves there, the really smushed together ones. So you see underneath it, you have atomic nuclei. And then on the left-hand side, you have radio waves about the size of buildings. And so it works its way up. Also notice down the bottom between the 10 to the 12th and the 10 to the 15th frequency, you have colors. So colors all have different wavelengths as well. So red has the lowest, and purple or indigo has the highest. When energy is transferred by a wave from a vibrating source to a distant receiver, no matter matter is not transferred. It's just the energy moving between the 2 points. So example, string, disturbance moves, but not parts of the string itself. So the string stays in your hand and attached to the wall. It's just the energy in the movement that moves, not the actual string. Drop a stone in a quiet pond and you'll produce a wave that moves out from its center in expanding circles. The disturbance moves, not the water itself. Okay, so it's just the disturbance, not the actual substance moving. Those are also called concentric circles, by the way. When someone speaks, the sound wave is a disturbance in the air that travels across the room. So the air molecules are not moving around. It's just the disturbance that moves. So the air, like the rope and the water in the previous examples, is the medium through which the wave energy travels. Energy is not transferred by matter moving from one place to another within the medium. Okay. So I think I'm going to end it here. All right. And I'll get back to you later with the next one. Thank you.